So welcome back as we move on through chapter 24. We just practiced comparing or looking at a mean, and now we get to the more fun stuff of comparing means, which is much more useful. As you guys know, the homework is going to be due later this week. Also, make sure you work on the quiz and the free response question. We're going to break this chapter into 3 bits, and then I hope to give you a lot more practice problems as we move forward with this. Our objective is to use students' t-test, null and alternative hypothesis about 2 population means. And when it comes to testing, we use confidence intervals and tests. So we'll get used to that. The intuitive display for comparing 2 groups is a box and whisker plot, and of the data of 2 groups arranged for easy comparison, like so. If we take a look at this box plot, which I will show you guys how to do on your TI Inspires, we're just looking at regular versus honors. We can see that the regular aptitude scores on this scores on this aptitude test are a lot more concentrated, whereas the honors group is more spread out, but it has a higher median, which also means it probably has a higher mean. We should remember what our 5-number summaries are. I'll just write that in there. 5-number summary with our box and whisker plot. So we have Q1, Q3, our median are 1.5 IQR plus and 1.5 IQR minus. Also remember that if there's a number that goes on the outside, we usually indicate it with a star, and that's going to be one of our outliers. So just as a recall from what we covered earlier in the course. Of course, the means of 2 groups are not part of the display, but the comparison will give you a heads up when comparing means. So next up, we've spent some time comparing proportions for 2 groups. Comparing 2 means is very similar to comparing 2 proportions. So this should be relatively easy for us. The parameter in these cases is the difference, and I highlight that again. We are looking at the difference between the 2 means. And remember, for independent random values, variances add. This is the Pythagorean theorem of statistics. If you do know the standard deviation of your populations, the standard deviation of the distribution of difference between the 2 sample means is, we take our averages, so standard deviation, the difference in our averages is equal to the square root of sigma squared 1 over n1 plus sigma squared 2 over n2, which should look familiar. But when you don't know the true standard deviations of the 2 groups, we use the standard error. So we use standard error when we don't know the standard deviations. And standard error, as opposed to standard deviation, we use SE. The difference in our averages is equal to the sample standard deviation squared over the sample size plus the sample standard deviation squared of group 2 over the sample size. When working with means and the standard error of the difference between means, the appropriate test statistic for sampling model is students t. We build a confidence interval called a 2-sample t interval for the difference between sample means, and the corresponding hypothesis test is called a 2-sample t-test. So when you don't know the population standard deviation, we're going to use students t interval and students t-test. This is what it's going to look like on our calculator. Hopefully you get a lot of practice. So for a 2-sample t interval, you either have stats or you have data. Same thing for testing 2-sample t-test for means. We either have our stats, so we use the statistics given, or we use the data that we're given. So when our conditions are met, the standardized sample difference between the 2 means, between the means of 2 independent groups is, and this is just like we had for our t statistic before, only this time we have our difference in sample means, and this is our difference in population means. And I just want you to recall, especially when we're doing hypothesis testing, this is going to be almost always 0. And then we have our standard error below. Modeled by students t with a number of degrees of freedom with a special formula. I'm going to say a note to this. We're going to use the calculator for this formula to get our degrees of freedom. And we estimate the standard error with our standard error formula. So what are the assumptions and conditions that we have to check now that we are comparing 2 groups? Well, again, we're going to check each of these for both groups. And here's our standard run of the list. So do we have the independence condition? Is there randomness condition? Were the data collected with suitable randomization? Was it a representative random sample or randomized experimental assignment? Do we meet the 10% condition? This condition is rarely applied for differences of mean. Check it for means only with very small populations or an extremely large sample. This is rarely checked just because we usually get this. Now, next one, the normal population assumption. We need to check that each of the pieces that we're given is sufficiently normal. So you must check this for both groups. A violation by either one violates the condition. We do this by checking a histogram for both samples. The last one we have to check is the independent groups assumption. The two groups we are comparing must be independent of each other. For dependent groups, there is a special test that will be covered in the next chapter, and that's where we have our sample paired test. So once we meet our conditions and we want to run a two-sample t-interval, we find the confidence interval for the difference between means for two independent groups is, we write the difference in our averages, plus or minus the critical value, times the standard error. And again, to calculate standard error, it's our sample standard deviations squared over each one of their sample populations. So the critical value, or t degrees of freedom, depends on a particular confidence level, C, that you specify on the number of degrees of freedom, which we get from the sample sizes and a special, very complicated formula. If you want, you can zoom in onto this notes and you can see what this formula is. I'm not going to necessarily require you to do this. So because of this, we will let the technology calculate the degrees of freedom for us when we find a two-sample t-interval and two-sample t-test. Remember, I have urged you to run the test first, and then we do the calculations by hand. Run test first, then calculate by hand. The hypothesis test that we use for comparing two samples is not surprisingly called the two-sample t-test for means. The conditions for a two-sample t-test for the difference between means of two independent groups are the same as for the two-sample t-interval. We test the hypothesis, so our null is going to be the difference is going to be our delta. So that's our Greek letter, where the hypothesized difference, so we say delta null, is nearly always 0, using the test statistic. Now, the two things that I need you to provide, here is our normal model with our mean of 0, that's our difference of our means, and our standard error for our standard deviation. The other thing that you will provide me is your t statistic, and this is what we are going to compare against our critical value. We always compare t to the critical value. Same thing with z. So let's try one of these. A study was conducted to compare college majors requiring 12 or more hours of mathematics to majors that required less than 12 hours of math. The mean income of 8 randomly chosen majors requiring more than 12 hours of math was $45,692 per year, with a standard deviation of $1,236. The mean income of 10 randomly chosen majors that required less than 12 hours of math was $40,416, with a standard deviation of 5,324. Test for the difference in incomes at an alpha level of 0.01. So something that I might want you to think about, that I'm not going to give you the answer right away. What sampling method do you think was used in this study? I mean, we could pull up a list of any college, see all of the different majors. We can compare our two lists that we're going to have to separate from majors that require more than 12 hours of math to majors that require less than 12 hours of math. That should give it away what we are doing right here. We will test the difference between the sample means and compare it to a hypothesized population difference of 0. What we are going to hypothesize here, as I zoom in, our null hypothesis is that the average salary for majors that have over 12 hours of math is going to be the same as the average salary of majors that require less than 12 hours of math. With our alternate hypothesis is that the means are different. Or we can think about it this way. The difference between these two is equal to 0. And our alternative is that the difference between these two means is not 0 or is different. So I'm going to just use this. If you have mu greater than 12, that is the mean requiring 12 or more hours. And then the mu with less than 12 is equal to the mean requiring less than 12 hours. So let's go through and check our assumptions and conditions. So, independence assumption. We have met the independence condition. The individual majors are independent. The randomness condition, it says that the majors were randomly selected. 10% condition, 8 and 10 are definitely less than 10% of the majors offered. Next up, our normal population assumption. So our samples are small, but it is reasonable to assume that salaries, because that's what we're looking at in this distribution, are normally distributed for all majors. And last up, independent groups assumption. The two groups are independent of each other. And that's true. You either have a major that's less than 12 hours or you have a major that's more than 12 hours. They can't be both. So now we will conduct a two-tailed, two-sample t-test for our model. And it's important that you write out your model, as always, with the difference in the means being 0. That's our hypothesized difference. And our standard deviation, our standard error of 1,739.3848. And this again is calculated by the square root of S1 squared over N1 plus S2 squared over N2, which is also given on our calculator. So this is where we jump to our TI Inspires, or if you have a TI 84, this should walk you through it. So we're going to go to Math. We're going to pull up a calculator. We're going to hit Menu, Stats. We're going to go down to Tests, and we're going to select two-sample t-test. We're going to type in our average for our first population, 45,692. Our standard deviation is 1236, and our sample size is 8. Our average for our second population is 4416. Our standard deviation is 5324, and our sample size is 10. Now note, we're going to do a two-tailed test, so we are looking if they're not equal to. We are not pooling, and so we type in calculate. And when we calculate this, we're going to get our t-value, our p-value, our degrees of freedom, and this is what I want you to highlight. Degrees of freedom, we are not going to calculate, but this is where it comes from. Then we have our averages and our standard deviations and our sample sizes. So here's our results. What should we conclude from this? So to remember, to calculate the test statistic once we've run this data, so we have these, so our numbers should match. To find our t-statistic, we have our differences in our averages minus the difference in our means. And again, this is 0 divided by our standard error. So if we plug in these values, we get 45,692 minus 4416 all over our standard error. And this gives us 3.033. I'm not going to ask you to find the degrees of freedom, but if you need to, it's on this slide. So the t-score we calculated is 3.033. And if we look at our critical value, using our degrees of freedom that we found, remember to find our critical value, use inverse t. Our area is going to be 0.995 because alpha was 0.01. Our degrees of freedom is 10.194, which is what we previously calculated, and we get a critical value of 3.1558. And what we're looking for is what is the probability that our t-score is greater than 3.033. Well, if we look, the t-score that we got is 3.033. That is definitely less than 3.1588, which is our critical value. Or another way to think about it, the p-value that we got is 0.012, and that is definitely bigger than 0.01, which was our alpha level. And if we look at our picture, because we're always going to draw a picture, there is our normal model centered at 0. And we're looking at, does our t-value fall in our significance level at the two-tailed test, so it's 0.005 on either side, and our t critical value of 3.1588. Looking at all of this, this comes to a conclusion that because our p-value is greater than our significance level, we fail to reject the null. There is not sufficient evidence at the 0.01 level to suggest that the mean income for majors requiring 12 hours of math is different than the mean income for majors requiring less than 12 hours of math. And just as a note, this is why it's so important, the choice for your significance level or your alpha level. If we chose an alpha level of 0.05, this would be statistically significant, but we want to be even more precise, so we set a 0.01 level because we want to be really sure. So that takes us to the end of our first video. We're going to do one more video of calculator practice, and then we're going to wrap up this chapter.